Dear student, today we will learn about the power electronic switches. Power electronic switches, or it is called the semiconductor switches, or it is called the semiconductor devices. These are the fundamental component, or you can see it is the backbone of power electronics, which is playing a crucial role in controlling and managing electrical power in a wide range of applications. These devices are designed to handle high voltages and currents, making them essential components in power electronic system. Power semiconductor devices are semiconductor devices used as switch in power electronics applications. They are designed to handle high power levels, typically above 1 watt, and are used in variety of applications, including power supplies, motor control, and automotive system. Now in the recent times, power electronics is very useful for the EV system also. The importance of the power semiconductor devices lies in their ability to efficiently control and manage electrical power, reducing energy losses and increase system reliability. So first we will learn about the ideal switches, and then we will learn about the practical switches. So ideal case, if we consider that if for off state means when the switch is in off position. So within this off position or off state, if the two side is point A and point B, so the potential difference between this A and B, suppose it is V switch, VSW. That means a voltage source is connected with it, but switch is in off position. So what is the voltage it can withstand, or what will be the voltage across this open circuit? So this open circuit voltage is the same voltage that is appeared across this switch. So that is the V switch. In the waveform you can say in the red line, T off here mentioned that the off time means the switch has a two state. One is on state and it is off state. Off state means when no current is flowing and switch is in off position. So at that moment the voltage will be the same, that is applied across the switch and no current is flowing through it. So this is the ideal case. On the same times, if you consider on the on state, means when the switch is closed, so it has a path, so current can flowing. This I switch is the current flowing through the switch. Okay, so in this on state, it can say that there is no voltage drop, so current can flow from the A point to B point. Okay, next. So if I draw the waveform of it, you can see that during the T on time period, I switch will be positive and it has a finite value, and this time T on, the voltage across the switch is 0. Okay, and during the T off time period, current is 0 and voltage has a finite value. Finite value means which is connected across the switch. So what is the power loss for the T on and T off time period? So you can say that when this is a T on time, current is flowing through it but no voltage, so it will be 0, and the T off time period, when there is a finite voltage but current is 0, then also the power is 0, power loss is 0. So you can say that during ideal case, or in the ideal case, the power loss during on state and off state of the power electronic switches is 0. So what are the conclusion we can draw from the ideal case? No leakage current during off state, means when there is a T off time period, no leakage current can flow through it. No voltage drop during on state. So when it is in on state, there is no voltage drop across it. And no delay during state transition, means when we start the stop or on, instantaneously it will off or on. There is no delay. That means no rise time or decrease time of current and voltage. So no delay during state transition. So what we can conclude, that there is no power losses. These are all for the ideal case.